Cool. So welcome back, everyone. We're going to have our last but not least invited talk. The talk is going to be given by Nick Rhinehart, who is a postdoc working with Sergey Livnin and others within the UC Berkeley AI Research Lab. He received a PhD in robotics working with Chris Catani at Carnegie Mellon University. And one of the main goals of his work is to create useful and general learning agents that make complex decisions by forecasting the long-term consequences of their actions. So today he'll be presenting on some of his work towards this vision of learning to forecast everything.
Great, thanks for the introduction. And yeah, thanks for having me at the workshop. I'm really excited to talk about what I've been working on. Today I'll talk to you about several of our efforts on building capable decision-making systems by forecasting. Why should we forecast? We can take motivation from the natural sciences. They seek to build understanding through testable models of cause and effect. These models make predictions about what the observations we should see, and if the future they predicted comes true, we say the model is useful. For example, different models of gravity have been used to plan rockets to the moon and predict gravitational lensing. Morphogenesis models predict patterns of many natural phenomena, like fish scales and population dynamics. The empirical sciences structure understanding of the world through prediction. Another source of motivation for forecasting is human intelligence. Humans often structure their world around prediction. I claim that in order for an agent to be intelligent, it must have a reasonable idea of how the future will unfold. Humans process rich observations of their environment in order to understand and to behave. For instance, we have the capability to predict and plan actions necessary to walk. We strive to predict how our competitors will behave. We can predict and plan socially acceptable driving behaviors. Our success generally depends on our ability to forecast. We usually fail when we cannot. It's worth noting that humans are particularly good at predicting the behaviors of other agents. Much of my research stems from my belief that in order to build intelligent agents that behave well, we must enable them to predict the future. I'll talk to you today about my efforts to computationally model the future in the presence of agent behavior given rich observations of the environment, like images. I'll describe our goal in terms of a decision-making system that we want to build. It should process high-dimensional observations of the environment to forecast sequences of multi-agent behavior. We should be able to direct this system by providing it with high-level goals to yield interpretable plans of behaviors that we then execute in the environment. The design of the system is then mainly a matter of designing how and what to forecast and plan. Imagine you want to safely drive through a busy urban intersection in an unfamiliar city. You're not sure where the other drivers want to go. You're not sure whether there are pedestrians hidden behind the other vehicles, and some of the vehicles look unfamiliar to you. In order to achieve this task, you use information from your eyes, your ears, and your past experience to devise a safe plan that accounts for all of your uncertainties in what might happen in the future. Your plan is contingent. You have different behaviors planned for different possible futures. Furthermore, you're able to adapt to predict that the unfamiliar vehicles will still move more or less like vehicles without any human telling you so. An autonomous solution to the same task should extract all of the relevant information from all of the sensors into a compact and actionable representation. The representation and model together should enable the system to accurately predict how its actions will affect the world while maintaining uncertainty about parts of the world state that haven't been observed yet. How are we going to do this? First, we must enable the system to perform contingency planning with its representation by modeling the consequences of its actions. Next, we need to determine what the representation should be. Should the system construct its representation out of human-labeled entities of interest in the training data? I don't think it should. Why not? Well, The system will always encounter entities that defy precise type categorization. Second, labels are much more expensive to collect than raw sensory data. And third, we have evidence that it's not necessary. Animals manage to make complex decisions just fine without human labels. I think the system should instead forecast everything, all of the sensor data available to it. In the autonomous vehicle setting, this means forecasting things like LiDAR and videos. Our goal is a system that can perform contingency planning through this model, learned to forecast sensor data. Today, I'll talk to you about two efforts towards these individual components: contingency planning and sensor data forecasting. What is contingency planning and why should we use it? Contingency planning allows for a robot to consider its ability to react in the future when deciding what to do now. This decision tree I'm showing here represents an autonomous driving scenario of possible sequences of robot and human decisions when a robot is trying to make an unprotected left turn, in which it does not have the right of way in an intersection, and it must wait for the oncoming car to either pass or yield before turning. If the robot were to decide ahead of time a deterministic series of actions, that is a non-contingent plan, it would prefer to wait outside the intersection and never arrive early because it cannot resolve the uncertainty of the human with a deterministic series of actions, or rather it cannot handle the uncertainty of the human with a deterministic series of actions. Instead, if the robot was overly confident in its ability to make the human yield to it, it could produce a plan that always turns before the human, but it may lead to collisions in reality when the human doesn't do what the robot planned for it to do. However, with a contingent plan, the robot can potentially arrive earlier by planning to enter the intersection first with a contingency plan for different behaviors it may observe the human to do. If the human chooses to yield, the robot would proceed to make the turn. Otherwise, the robot waits for the human to pass. Why is contingency planning difficult? It requires a few key ingredients to work well in general settings. It requires a model of interaction between the agents. It requires the ability to use this model to produce contingent plans. And it requires the model to be seen conditioned, because the behaviors of the other agents, as well as the goals of the robot, both generally depend on the context of the environment. Our goal is to make contingency planning tractable by learning a latent planning space where open loop latent plans correspond to contingent plans when combined with the uncertainty of the other agents. This will enable end-to-end contingency planning from high-dimensional observations of the environment and should minimize the engineering burden of planning in arbitrary scenarios. We have as input to the model the single robot latent plan, as well as some scene conditioning. The model incorporates as input uncertainty about what the other agents may do. For one realization of what they may do, the single robot plan results in a specific joint trajectory. For a different realization of what the other agents may do, the single robot plan results in a different joint trajectory. If we can design a model in this way, the challenge of contingent planning is reduced to the challenge of identifying a single robot plan in the planning space that results in high quality trajectory space plans and expectation. This planning space corresponds to a small set of free parameters of a robot policy. The policy is a contingent plan for what may happen in the future. Once the free parameters are specified, again, the robot's policy is fully specified and corresponds to a contingent plan. We implemented various scenarios that require contingent planning in the Carla simulator. On this slide, I'll present videos of each of the possible outcomes in the left turn scenario. The first video shows the outcome in which an aggressive robot turns unsafely in front of a human, and the human is unable to yield in time. The second video shows the same aggressive robot coupled with a human that is able to yield in time. The third video shows a passive robot that always waits outside the intersection for the human to pass. The fourth and fifth video demonstrate a contingent robot that nudges into the intersection in order to observe whether the human will yield to it and react differently based on the human's behavior. The contingent robot safely and quickly arrives at the goal more frequently than the non-contingent robots, those on the top row. Okay, and here's just another visualization of the method with the frontal view of the car. We also had created several other scenarios, including a right turn scenario. It's more or less the same as the left turn, except the oncoming agent has no stop sign, whereas our agent does have a stop sign and needs to decide whether or not it can turn in front of the other agent. And then finally, we have an overtaking scenario. The robot is trying to overtake the human by switching into the left lane. While the human may slow down to facilitate the overtake, it could also choose to speed up to prevent it. The robot must then act accordingly. Here, again, the behaviors are consistent with the decision tree we presented earlier. In our setup, we have these overall behaviors programmed as scenarios, and then in each scenario, we evaluate it in many locations. Okay, so here's a method overview of the method from model training to deployment. The model is learned from two inputs: multi-agent demonstrations of behavior, essentially state space agent trajectories that have been labeled, and observations of the environment, usually high dimensional observations. And in our application, we used LiDAR range map images. At the deployment phase, the robot repeatedly plans using the contingency planner. The contingency planner has a planning criterion that scores joint trajectories, and I'll discuss this later. The planner also receives observations as well as past trajectories from the environment, and as well as some goals from a higher level planner that tell it where it should go. The end product of the contingency planner is a policy. The policy is used to produce the next target position of the robot, which is then fed to a simple positional controller on vehicle throttle, brake, and steering. The controller executes for one or several steps before repeating the above planning procedure. Okay, so how are we going to learn this model, and how are we going to use it in the contingency planner? At the training phase, we learn a deep likelihood-based model of multi-agent behavior by training it to forecast trajectories via a maximum likelihood objective. It's important that this model has a likelihood associated with it, because that likelihood will be incorporated into the planning criterion. Here is just a kind of a sketch of the network architecture. It processes the LiDAR information, and at each step, sequentially rolls out an RNN for each agent that receives information from the most recently predicted positions of the other agents. This diagram maybe isn't so important to what we have here. Suffice to say, it's a neural network, and there are many ways you could design it, but the two key elements are it's likelihood based, and it factorizes over the number of agents that you have. Okay, now with this model, a closed loop policy can be represented by specifying the free parameters of oh, I think I forgot to mention. Let me just go back here. So the form of the model can be equivalently seen as this collection of policies, of stochastic policies. These policies react to the predicted future behaviors of all agents. These policies become deterministic when you specify or give a value, a realized value of the uncertainty of each agent at each time step. So we can view all of the model parameters as the fixed parameters of a deterministic policy, and the free parameters as the uncertainty that when you specify it, the policy becomes deterministic. With a deterministic policy, the agent has a specific set of reactions for all eventualities of what the other agents may do. So it's still a contingent plan, it's just deterministic. The plan parameters are optimized via a gradient ascent, stochastic gradient ascent on a planning objective that we designed. The objective rewards plans that have high likelihood under the behavioral prior, meaning that the trajectories are likely to have occurred in the data. It also incorporates a destination by awarding plans that result in trajectories that come close to the goal, specifically robot trajectories that come close to the robot goal. Lastly, it penalizes for any constraint violations like near collisions. And then the objective is to plan high quality plans under the expectation of the uncertainty of the other agents, essentially in expectation of what the free parameters of the other agents could be. In our experiments, we also find that opposed to gradient ascent, we can also just randomly sample a large number of latent plans for the robot. And that serves as a pretty good approximate maximization objective, approximate maximization method for this planning objective. Okay, so if we return back to the diagram that describes the goal of our system, we see that the uncertainty of the world is a distribution over the free parameters of the other agents. And the latent plan for the robot is the specification of its free parameters. Together, these are transformed by the model to produce a joint trajectory, one for each realization of the uncertainty of the other agents. Okay, so let's go back to our left turn scenario. Here are some examples of non-contingent behavior on this task. What I'll call an overconfident planner will use our model to assume the human driver will always cooperate. This results in aggressive robot behavior. Oh, looks like I'm showing the underconfident model there. That's too bad. Okay, so let's talk about the underconfident model. The underconfident model, what it corresponds to is assuming the robot can only control its future state space trajectory. This planner is aware of the uncertainty of the other agents, and there's no state space trajectory that can reliably take it through the intersection quickly. So essentially, it results in an agent that waits outside the intersection for a long time until whether or not the human would yield is resolved and the human actually just goes through the intersection. So this underconfident planner just arrives late to the goal. Okay, here are some examples of contingent plans visualized in this left turn task. So on the left, this contingent plan is for the instance of when the human does not yield. And then the robot's plan in blue is to wait for the non-yielding human. And then on the right, the contingent plan results in a joint trajectory where the robot turns in front of the human. Now, these contingent plans correspond to a single specification of the robot's latent space plan beforehand. And these are just two of the possible, essentially infinite outcomes of what joint trajectories could result in reality for corresponding to 2 of the possible ways that the human might behave. Okay, and then in the overtaking task, we see something similar, where the contingent plan is contingent on whether or not the human will yield to it. So in the case where it expects, where the uncertainty of the human being realized results in the human yielding to the robot turns in front of it. Otherwise, it backs off, trying to overtake the human, and gets back into the right lane behind the robot, or behind the human. So we set up an evaluation of these 3 scenarios in various locations within the Carla simulator. And it was particularly tricky to set this up because a lot of the situations in which contingency planning is necessary in Carla are resolved by having most of the intersections being signaled. And essentially there are very specific cases in which non-contingent planning leads to failure. And often you can kind of, you can still get good behavior by executing a non-contingent planner in situations where you can easily recover. So we needed to design situations where you can't recover from executing a non-contingent planner. So, whoops, these videos play. Right, okay, so these are just visualizations of the contingent robot in each of the 3 scenarios again. And so what we found is that essentially in these scenarios, the contingency planning was necessary, and that our method was able to perform contingency planning in these scenarios. So if you take, for instance, something that doesn't model the future behavior of the other agents, it cannot incorporate that constraint term, the no collision constraint. And so if you behave just according to the data that you observed, which includes some of these sort of risky scenarios, you will result in this single agent approach that results in sort of this risky behavior half the time, because half the time the human does not yield. And then with these other non-contingent planners, with the underconfident one, you can never get to the goal quickly, but you can always get there reliably. With the overconfident one, you can always get to the goal reliably, but not always safely. Essentially, this RG star is measuring whether or not you got there quickly and safely. And then for the times that the human does not yield, you don't get there safely. Okay, so to summarize, this approach enabled us to perform contingency planning with a learned model, but it relied on trajectory labels for the entities of interest. And I think we should develop a more general approach. In this next work, I'll discuss separate work on trajectory forecasting that first forecasts everything, by which I mean it forecasts likely future sensor inputs. So let's start by discussing a standard perception and prediction pipeline for decision-making in multi-agent environments. This pipeline receives sensor data, it runs object detection and tracking on it, and then it uses the detections to perform trajectory forecasting of the resulting objects. Each stage in this pipeline requires human annotated data of what and where the objects are. In an autonomous vehicle setting, the sensors commonly include LiDAR and RGB images. After receiving the sensor data, object detection is performed. Here, vehicle detections are shown. Then multi-object tracking is performed to associate the detections over time. And finally, the tracks of each object serve as input to the trajectory forecasting component. The main question we examine in this work is whether the final stage in the pipeline is really the best place to be performing prediction. Maybe instead we can forecast futures of objects that don't retain temporal information. That's probably not a great idea. But what if instead we forecasted future sensor data? Then we apply the object detection and multi-object tracking, not to the received past sensor data, but to the forecasted future sensor data. So let's compare these two pipelines. On the bottom left, we have this conventional pipeline. The sensor data is consumed to produce object trajectories. And then these object trajectories serve as input to a module to forecast future object trajectories. In our proposed alternative pipeline, the sensor data itself is forecasted and then consumed to produce object trajectories. So this inverts the order of forecasting and object detection and tracking. Why would we want to do this? Well, first, there's no bias on what to model. By predicting everything, the model has to develop a holistic understanding of the data. By not relying on human labels, categorization errors and missing data errors common in label data cannot affect the forecasting model. Second, without these labels, the forecasting component can be scaled. That is, we should generally expect to be able to improve the overall performance by simply adding more unlabeled data to improve the sensor data forecasting component. Okay, so what we have, we can break things down into sort of two separate tasks. First, it's the scene point cloud forecasting task. And then after that, it's the task of post-processing that sensor data to trajectories. So let's talk about the first component of the task. In contrast to trajectory forecasting of agent poses, which is typically produces some number of 3D poses of some small set of objects in the scene. The point cloud forecasting instead output is much higher dimensional. So the point cloud at each time step in our settings contains over 100,000 points. So we just set up the problem to consume a length m sequence of past point clouds and produce a length n sequence of future point clouds. Each frame has a variable number of inputs, often above 100,000. And our model is a straightforward encoder-decoder framework. It encodes a sequence of past frames with a learned encoder coupled with a recurrent neural network, and then decodes them to serially produce the future frames. In the simplest variant, we just use a range map encoding of the point clouds. So this is as input to the encoder. A range map represents a variable sized point cloud as a fixed size array of points and polar coordinates. It then transforms the incoming scene point cloud, represented as the range map, with a learned convolutional neural network to produce a single output feature for that range of, for that point cloud. It's trained with the chamfer distance loss, which was proposed in a paper on generating different kinds of point clouds for small objects. And it's also trained with an L1 loss on the output range map encodings. So from this initial model, here is a comparison of, on the top, some ground truth of future LiDAR sequences, and then on the bottom, the outputs of the learned model. So you can see that the point clouds actually look pretty different. The key difference is actually that small objects are not really represented very well. In some ongoing work, we've started getting better results with smaller objects, much better results, just with some straightforward architectural improvements. So what we did was we first evaluated the quality of the scene point cloud forecasting, that learned model, versus a few baselines we designed, and we find the model performs well. And then more importantly, we take the resulting point cloud forecasting model and then apply an object detection and object tracking post-processing scheme to the resulting point clouds. And what we do in our evaluation is that we evaluate existing trajectory forecasting methods using the same object detection and trajectory and object tracking components. And we found that when you evaluate the whole pipeline, the result on these data sets and for these time horizons was our method actually performed better. Here is a visualization of the tracking on the point clouds. I'm going to kind of skip quickly to get to the conclusion here. This is just visualizing some improved architectures we've been experimenting with on the bottom right here. Cyan is small error and red is large error. So you might notice that this model was deterministic, which precludes it from being used as a contingency planner because it does not incorporate the uncertainty over what the other agents may do. So essentially, to combine them, the next step is to take these ideas from contingency planning and take these ideas from the sensor data forecasting and combine them. And that is what this talk was towards. Thank you.
Thank you so much, Nick. We're a little bit short on time, but I definitely want to allow for at least one question from the audience. So if no one else has a question, I have one for you, Nick. So this is in the spirit of our workshop theme this year, which is not only discussing all of the successes that people have been making, but also talking a little bit more about where there's room for improvement. So you showed these really neat results for your contingency planner. And it seems very intuitive and it seems very successful in the examples you showed. Can you give us any insights as to maybe where contingency as it stands right now is just not sufficient?
Well, so the model still requires access to a large set of training data, and then for it to generalize, you kind of need a broad coverage of the set of scenarios you might encounter. And that was a huge challenge, just working with the Carla simulator, because we essentially had to create these settings where we could precisely evaluate when contingency planning was necessary. And so to really have a good understanding of whether or not it's performing well in general, you kind of need a larger benchmark to evaluate settings where contingency planning matters. Yeah.
Cool. If there are no other last comments or questions for Nick, I
do have a question.
Oh yeah, go for it.
Okay. It's related to the first part of the talk. So thanks, Nick, a really interesting talk. Regarding the first part, does this method apply also for multi-agent systems? So you have tried only like, with a pair of agents. I don't know if you have, maybe if you had the chance to test it with a single ego vehicle, but across, I don't know, dozens of agents. I'm just thinking, if one can apply a similar method into, robot navigation, where we have robots which are navigating through crowds of people, for instance.
In principle, yes. So the underlying model we used was a model of essentially a variable number of agents. Yeah, you can, it does incorporate uncertainty over a number of agents, but of course, like the question is whether or not it scales. So I think it would be possible to engineer it to scale, but without, again, like settings on which to evaluate it. Maybe you're familiar with some that I'm not, but it's hard to say whether or not it would generalize.
Mm-hmm. Okay, thanks.
We have one last hand raised from Lucas.
Yeah, thanks a lot. So I was just wondering on the last part that you showed, essentially predicting the data. There was like, I think it was very short video snippet where you actually were able to predict or perform actually object detection on the predicted data. I like, from what I saw, it looked fairly difficult. Are you actually able to reliably do object detection on the predicted data?
Yeah, so with that model that we presented, it is possible to do object detection. Basically, the model does retain large object information by nature of its training objective. And so while it was losing some of the smaller objects, you actually have sufficient information for performing object detection. Although one caveat is that I'm not sure exactly. I think that the object detector that we used was not just based on some heuristics for given a point cloud output the poses. It was learned as it is in existing pipelines, but this learning can occur on a frame-by-frame basis. It essentially doesn't need the trajectory tracks. So to get to the resulting, you could use an unsupervised detection method on the resulting point clouds, but it would probably require something like what our newer models are getting towards to have the kind of quality to perform that unsupervised detection.
Okay, cool. Thanks a lot.
Awesome. I am going to turn it over now to